Example 4 should look similar, or should look familiar, since it's exactly the same question we answered in example 1. So we still have, or can still label each of these equations as 1 and 2, but now what we want to do is solve the same system using elimination to demonstrate that method, but also reinforce this idea that for linear systems, these two methods are interchangeable. The idea of elimination is that we want to add these two equations together in some way so that one of the variables cancels out. In this case, that's really easy to do because we have a positive y in one equation and a minus y in the other equation. So without updating anything, we can add these two equations together and our y's will just naturally cancel out. So x plus x is going to give us 2x. Y minus y is going to give us 0, and then 4 plus 2 would give us 6. So we would have 2x is equal to 6, or dividing by 2 would give us x equals 3. Once we have that result, then we'll substitute into equation 1 or 2, and then solve for the remaining variable. So in this case, I'm going to choose to substitute into equation 1. We already came up with a value for x, which is 3, plus y is equal to 4. Subtracting 3 to the other side will give us y is equal to 1, meaning we come up with the point of intersection as 3, 1, which again is an answer that we already knew, but demonstrating that we can use that use this elimination method interchangeably with the substitution method. In example 5, we have a slightly more difficult case to consider because we can't just add our two equations together. If we do, we would still have both an x and a y term left over. So referring to these again as equations 1 and 2, what we can do is look at updating one or the other equation in some way so that when we add them together we do end up with a variable canceling out. What I'm going to choose to do in this case is take every term on both sides of the first equation and multiply by 3. Since I'm performing the same operation on both sides, I'm not changing the truth of that statement. But now we have a new equation, 12x minus 3y is equal to 33. And our second equation remains unchanged. And our result in doing that is that now we have minus 3y plus 3y, meaning those y terms will cancel out, which is exactly what we want. One of those variables to completely cancel out. So we'll end up with 19x plus 0 is equal to 76, or dividing both sides by 19 will give us x equals 4. Again, there would be different ways to start this off, but we just need to look at multiplying the one or both of the equations by some value so that our end result gives us a pair of variables canceling out with each other. Once we come up with that value of x equals 4, then we can substitute back into either of the original two equations. This time around I'm going to substitute into equation 2. So we'll have 7 times x, which we've already found to be 4, plus 3y is equal to 43, which will give us 28 plus 3y is equal to 43, or 3y is equal to 15, which means y would be equal to 5. So this gives us our point of intersection for these two lines occurring at the point x equals 4, y equals 5. In example 6, we again need to look at updating one or both of our functions, or one or both of our equations. In this case, purely through coincidence, Or actually, no, we'll go a different route. So in this case, what we'll do is take our first equation and multiply it by -3. We could have also multiplied by +3, which would give us a -3y, which would cancel with our 3y. In this case, multiplying by -3 is going to cause our x terms to cancel. So we always get some flexibility in terms of how we start off the problem. But multiplying both sides by -3 will give us -15x plus 3y is equal to 0. And then our second equation is remaining unchanged. So now when we add these two equations together, -15 and 15 will go to 0, so our x terms cancel out. So we'll get plus 6y is equal to 6, or y is equal to 1. So we use the same process, but this time we chose to cancel out those x terms. So initially we start off by solving for y. We can go back to our first equation and then substitute in the value that we found for y, and use that to solve for x. So this would give us 5x is equal to 1, or x is equal to 1/5, giving us the coordinate pair 1/5, comma 1 as the point of intersection between those two lines.